I'm hearing varying. Make sure it's log base 2.
It should be around 16.
Okay, somewhere in the 14 to 17 range. 17. 17, good, okay. Okay, 0.2. Right, so you already see, right, even this very short match at a very long distance, that is still saving you bits by encoding it. And like this 3 bits is not out of random, right? Like this is the 0th order entropy of English as we saw. I think it was actually roughly around 4 bits. So, right, so you see, the idea here is that far away short matches, even those are beneficial. Because it's so much cheaper to encode this 150, just the length 150,000 as compared to encoding the PLEASURE, these 8 characters, right? And you can like play with this more and actually like see that there will be like, as you might imagine, there will be a crossing point where it just, if you have a match of length 2 at a billion offset, that point you might say, okay, maybe it's not a worthwhile match, but still it is, like in this case, it is a worthwhile match. Okay. And we will just like gathered the data, try to look at like what is the distribution of match offsets and match lengths after you do this LG77 parsing for a particular implementation of LG77. We will see like it's not like a unique thing. So you see mostly you have smaller offsets and sometimes you have bigger offsets. So it's an exponential scale, right? So in this case, the longest offsets are around 150,000 because the text itself is around 150,000 long. And in terms of match lengths, you see oftentimes you see relatively small match lengths. Once in a while you see like match lengths more than 100 bytes, right? This is very important, like to understand that this is for this particular file. From file to file, from dataset to dataset, this distribution looks different, and that should influence what particular LG77 technique you use, as we'll see shortly. This is the CSS file we saw earlier, the one with the %, 50%, that sort of thing. Bootstrap min.css. Match offset maybe looks similar. Match lengths, you will notice here something different, right? There are some extremely long matches, more than like 500 bytes long, right? So you can do this for any file and just play with it, try to understand, right? Like if you imagine structured pieces of data like code, for example, would have a lot of matches of the exactly same type, like because the same keywords occur many times, right? The same variable names, the same function names. So that distribution will look different compared to text, where you have repeated words, but maybe not like repeated sentences exactly, right? If you have a table, like a CSV file, maybe some of the rows are exact matches of each other. So again, that's different from like text. If you have a random data, maybe you don't find any matches or you find very few matches. So this will be different for different data sets. Okay, any questions so far? Right. So just want to say one thing, that LG77 is like, I think today the most popular compression technique. It's the one that's most widely used in practice. To like do full justice to it, to explain even like how gzip works would take me several lectures, and to explain how something like Z standard, which is a modern version, works, would probably take me the entire course. Plus, I don't think I'm qualified to like actually talk so much about LG77, but we will try to look at some practical aspects of LG77, things that I'm more confident to speak about without bringing in like the creator of these algorithms. Okay, so first thing, this whole idea is very simple, right? But do I need to keep this infinite past memory? Do I need to keep all of the past at every time to find matches? Like if I have a 1 gigabyte file, do I need to like keep the last gigabyte in my memory and then look for matches in that last 1 gigabyte? That doesn't sound efficient, and people don't do that. What people do is use something called a sliding window LG77, where you only try to find matches in the last 10 kilobytes or a few megabytes, that sort of thing. Right? So you limit the scope. You don't look for matches that are arbitrarily far away. So that's one thing. And some technical details, like you can use circular buffers, some like particular techniques to efficiently handle windows without reallocating memory every time or moving a bunch of data every time. And we'll see this one in the next slide, that bigger windows give you better compression because now you have more, basically it's just making the compression encoder more powerful. Like it can find far away matches. But it needs more memory because then you need to store that entire window with you, both in the compression and the decompression. We have implemented this in SCL. I encourage you to look at it. It's, I think, well documented. And I had a hard time like actually finding an implementation that was like easy to explain. So I hope this will be useful, especially if you are doing a project on this. I will mention some like specific project ideas shortly. So I took the Alice in Wonderland book. I increased the window size like in an exponential scale. And I looked at the compressed size in bytes. So what you see is that as you expect, right, as you improve the window, you get better and better compression. At some point it starts leveling off, in this case because the file itself has a certain length, so making the window bigger than the file size obviously is not going to help. But even in general, after a point it doesn't help to have a bigger window. Again, this is something which is data specific. For your data, maybe bigger windows are better. Or for your application, maybe you can afford a lot of memory. So it's all about what you want to do. There are no like hard rules that always use 100,000 window. That's not the lesson of this plot. Another question, the basic question, right? We did it by hand, by eye earlier, but clearly like a computer won't do that. How to find matches? Match finding. This is like the core of a encoder, not the decoder. This is important to understand. No matter how you find the matches, the decoder can still decode your data. It's an encoder only property, this match finding business. How do I find a match in the past? And the basic idea, which again, you can find the code, is to, what you do basically is that you take like all of these different like common patterns, like the patterns that you have seen in the past, and you say that ABCD has occurred at position 1, position 10, position 15, position 20, let's say, and this guy has occurred at position 2 and position 14 or something, right? So you make this big table where each of these 4 length sequences, when have they occurred in the past? And now you are at some point in the file, you see an ABCD. So you see, oh, I have seen ABCD, past occurrences basically, are at 1, 10, 15, 20, right? Because you store this in like a hash table basically. So you store this table, which is like for every 4 length sequence, when have I seen it in the past for all possible sequences. And then when you find a sequence in the future, you look at its past occurrences and you try to see which one of them would give you the longest match. So maybe you saw ABCD at like position 10 in the past and at position 1 in the past. However, in this case, this was followed by EF. In this case, this was followed by like ZX. And here it's followed by EF. So you would prefer the first one, right? This seems a better match. This is a longer match instead of this one. So you have like a lot of candidate positions where this ABCD occurred. And then in the past, you look at where did you find a longer match to this ABCDEF. So this is like a basic idea commonly used in many algorithms, like a seed type idea, where to find a match, what you do is you take like a 4 length or a 3 length, 5 length seed. Seed is the thing you index in your hash table, right? So in this case, it's all 4 length sequences that are hashed in the sequence. You use that to find candidate matches, and then you find the best match out of those candidate matches. So really like reduces the search space when you're looking for things. So index past occurrences of sequences in a data structure like hash table, binary tree, you can choose your favorite. And for the given position, do a lookup to find previous occurrences and then extend the candidate match to find the longest match, right? So you extend it in the future, you see how long does it keep matching. Again, yep.
Should we just consider it not worth it matching 2 or like 3 substrates then?
So you are asking why I took 4 instead of 2 or 3?
Yeah.
Yes, that's a good question. there is a trade-off there, which we'll see shortly, but just to answer the specific thing, a two-length thing would give you a lot of false positives because you have seen AB much more than you have seen the ABCD whole thing, right? So now, if you are just indexing 2-length or 3-length, you will find many more possible things. So it will increase your complexity quite a bit just to like find all of the possible, to find the longest one. On the other hand, if you really work hard, you will actually find maybe a better match than you would find with a 4-length thing. So that's the trade-off basically. It will often make you slower, but maybe better compression. But in practice, we'll see even that is not true for a particular reason. But yes, if you make it too big, that's very bad because then you will miss out on a lot of matches. Okay, another sort of thing that's like not immediately obvious is that the LZ77 that we presented, like in the theoretical version, that is greedy. Greedy means that the first time it sees a match, it picks up that match. It doesn't think of the future. It doesn't try to do some complex optimization problem where, oh, maybe I should not take this match. Maybe I should take a longer match in the future. Let me give you an example. I'll make it very clear. So, okay. So let's say this is your sequence. At some point in the past, you saw like B, C, D, E, F. Let's say B, B, C, E, D, F, A, B, E, F, A, B, C, D. Okay, so now you're here. So the algorithm we were just discussing, you would see an AB. You will see, oh, I found a match to AB. And you will say, good, I'm done, right? Okay. However, maybe you can be smarter. You might say, okay, maybe I saw this match of AB, but it's too short. It's just of length 2. What if I skipped A? Let me skip A. Let me try to find a match starting at B. And suddenly I find a very long match. A match of length 5 instead of length 2. Right? So the first one is greedy. This one is like the first one is greedy because it just like takes the first thing and says, okay, that's it. The second one is lazy. Lazy in the sense that it says, okay, maybe I found a match, but let's not get too excited. Let's look a bit in the future. Maybe I will find a better match. Let's not pick it up right away. Does that make sense? Right? And as you can imagine, like the real like people who have looked into this didn't stop at this lazy, right? This seems like, okay, but how do you exactly do the lazy thing? They said, okay, let's make it into an optimization problem. Let's solve like a perfect optimization problem. Let's make a dynamic program out of it. And you can do a lot of things. There is something called optimal parsing. There is a big theory around it where what is the LZ77 parsing that gives you the fewest number of literals or that gives you the best compression. But they just get progressively slower and slower, the more complex your strategy is, right? So you can imagine greedy is very fast because you just take the first match, right? Lazy is slower because you don't take sometimes matches, then you try in the future, try to find a longer match and leave some things as literals. Is this concept clear roughly that sometimes being greedy is not the best option, right? You sometimes want to be a bit lazy, see if there is a better match in the future. Okay, so just to like show you like what a typical encoder would be structured like. So this is from the SCL class, sliding window encoder. So the encoder would take a match finder, which basically gives you the matches, and it would take a window size, which is the size of the window. And then the match finder would have like some way to extend matches, but really the main function is this, find best match, where given some sequence, it will try to find the best match. And there can be various implementation. You could have a lazy thing, greedy thing, just a bunch of different ideas there, optimal thing. And then this particular match finder we implemented, you see it has so many parameters. Hash length, which is like 4 in the example we were talking about. There's a hash table size because you don't want like an arbitrary large hash table. Something called max chain length, which we will not talk about. Whether you are lazy or whether you are greedy. Is there a minimum match length? So This is just like an implementation I did. If you look at Z standard or gzip, they have more complexities around it. But you can imagine that the really nice thing is that all of these are compliant with the same decoder. The decoder is not changing, right? We are just playing with the encoder, trying to find a better and better parsing of the data while using the best decoder. And that's a very nice idea because that allows you to, without breaking your consumers, people who are reading your files, they can keep using the same decoder, but you just get better and better compression by using these fancy complex strategies. Okay, are we happy? Or at least satisfied? Okay. Okay. So this is like an experiment I did where I had something called a minimum match length, which is like what is the shortest match I'm going to allow. And I kept increasing the minimum match length for again this Alice in Wonderland book. And what I'm showing here is that as I increase the minimum match length, I get more and more literals, but fewer and fewer matches. Can somebody roughly explain why that might be happening? So I'm basically rejecting any match that's shorter than a particular match length. Why would I see more literals as I increase my match length? Yeah. The answer is if you don't have a match, you have to store it as a literal, right? And now you're disallowing a lot of matches. Any short sequence you don't even allow as a match. So therefore you just get much more unmatched literals. And therefore you pay less to store the matches because there are just fewer matches, right? You only take very long matches. You say, no, short matches are not something I care about. However, you see there is a trade-off now because you get more and more literals, fewer and fewer. So there is like some sort of middle ground where you don't want your minimum match length to be too small. If it's too small, literals, everything matches, but then you have just too many matches. You have too many matches of like length 1, length 2, and those matches cost a lot. Maybe it's better to not have these super small matches, instead like use a bigger match and like leave a few literals. So there is a trade-off as in a lot of things. And then this is another thing I did where I looked at the lazy and the greedy strategy, again for this particular file, where the greedy strategy just picks the first match it finds of that minimum match length. The lazy strategy tries to go a bit further, sees if it can find a bigger match, and if it finds a bigger match, it takes the bigger match instead of taking the greedy match. And you see that the lazy strategy like always outperforms the greedy strategy in this case for any minimum match. So yeah, I encourage you to look at the code. I think only once you look at it and you think about it a little bit, you will appreciate this more and more. But the basic point I'm trying to make is lots of choices you can make at the encoder, which lead to maybe it makes it slower but better compression, or it takes more memory but better compression. So there are all these trade-offs. Any questions so far on this match finding? So one thing we tried to do in the implementation in SCL is we tried to, not like this here, try to separate the match finder so that you can like plug and play. You can try different match finders with the same encoder. The decoder doesn't change, just the encoder. You can implement your own favorite match finder. You can implement some DP, dynamic programming based thing. Okay. And then obviously you need to entropy code everything, right? It's not enough to just producing these is not enough, right? At the end of the day, you need to actually store it in bits. And that's again something people have played with a lot. The current sort of standard thing that everybody does, this is not what gzip does. Gzip does it a bit differently, but all the modern compressors do this, is you take all the unmatched literals in a block, you concatenate them together into like a single long thing, and then you store like the number here, 504, the length here. So really what you get, this is sort of a technical point, but really what you have is, you have the literals, which is a sequence of just like bytes, and you have 3 integer sequences, literal counts, match length, match offset. Very technical point, don't worry about it too much, but this is how everybody does it nowadays. And then you have to encode each of these, and we have all of the entropy coders we saw, right? So that's the power of these entropy coders, because all LZ77 is doing is converting your very complex stationary distribution into a much simpler IID-like distribution. So now you can use your favorite coders for IID distribution, and they will basically give you the results. Right. So you can use Huffman coding. gzip just uses Huffman coding. Z standard uses Huffman for literals. You can use TANS, which is like recently becoming more popular. C standard uses it for, not for literals. It uses for match lengths and offsets. Yeah. Or you can use context-based arithmetic coding, which is very slow to encode and decode, which is what LZMA or XZ or 7-zip, all these guys use. Or you could just skip entropy coding, say that, okay, I don't care. I will just use a simple code. I won't do like any fancy entropy coding because I want to be very, very fast. And that's what LZ4 and Snappy do. All these names probably don't sound very familiar to you. And that's fine. I think really there are only a couple of compressors you should know about really. And then everything else you can, if you need it, you look at it sort of. Let me skip this slide. It's like a technical point about how do you actually entropy code integers. Please read it at home. Okay, so really the lesson is that the parsing or match finding strategy, the window size, the entropy coder, implementation details like are you using SIMD, are you using these advanced instructions, are you parallelizing things, matter a lot in determining speed and memory usage. So let's look at this plot. So this is showing Z standard, which is a modern LZ77 based compressor, and zlib, which is the library behind gzip, which is an older, around like 30 years old now, compressor. The x-axis is compression speed, the y-axis is compression ratio, and where you want to be is on this side basically. You want higher speed, lower compression ratio, higher speed and higher compression ratio. And you see, and the different dots here are the different levels, like different parameters, where you take a bigger window or you use a more powerful entropy coder. You use a more powerful match finder. And you see that Z standard just like beats zlib on all fronts, partly because it has better algorithms, partly because it uses more memory, partly because it is implemented better to use modern hardware instructions. So all of these things matter. These small decisions end up like impacting where you lie in this curve basically. And this is decompression speed, where again Z standard achieves like amazing results. It's like 1.4 Gbps in this for some data set. Again, this is mostly because of how the decoder is implemented. That's a big role. And also because how they structured the format, which is a bit technical. LZMA uses arithmetic coding, so it's just very slow to decode, sadly. Arithmetic decoding, as we saw, is slow to decode. Another thing you notice is that we don't show any levels here, and the reason is that regardless of what match finding you use, the decoding stays the same. Decoding is just copying stuff from the past. So it affects it slightly, but not too much. The different encoders can still produce the same sort of decompression speed. And then, yeah, you can just like look at so many different LZ77. Each of them have their own levels from 1 to whatever. You have Z standard, zlib is gzip basically. You have Brotli from Google. You have LZ4 again from Jan Collett, who also wrote Z standard. You have Snappy from Google. So just all these guys keep making their own versions. And we look at like, for like a practitioner, how do you think about these? There are so many compressors, like you Google data compression, you get like 1 million results. What do you do? Before we go there, just a quick note that universal doesn't mean perfect, right? LZ77 is universal in an asymptotic sense. Like as n goes to infinity, it will achieve the entropy road for any stationary distribution. But your data is probably not infinitely large, right? It's a finite thing. So it need not be the best choice for your particular data set, right? Even if it is the perfect choice in terms of compression ratio, maybe it is too slow for you. Maybe it has too high of a memory usage, right? So all these things should go into your calculation. Just don't think that like LZ7 is universal, so that's what I will use. I will never consider any other compressor. That's not how we should think. And obviously, as we saw, right, gzip is LZ77, C standard is LZ77, but they are not the same. So there are a lot of like, beyond this base algorithm, the basic idea that works in theory, there are so many like minor things you can do or major things you can do which really change the world. Okay, so that's it on LZ. We didn't talk about LZ78. It is very interesting. I think I encourage you to read up on it or do a project on it if you want to. Tsachy covers it in much detail in EE274C. The course is called Universal Schemes in Information Theory. It's a bit like theoretical course. I think quite a while since it was last taught, but I think we can share the notes with you if you are interested in the theory aspect here. And there are a lot of things in LZ77, things like rep codes, optimal parsing, which we don't have time to cover here. All of these are good project ideas. Talk to us and we can point you to the relevant resources. Okay, so that's, so short, like the summary is that LZ77 is a great compressor, right? So now, but you have been like every compressor we teach you, we tell it's a great idea. Last time we said context-based arithmetic coding is great. Before that, Huffman was great. Everybody seems optimal in some sense. So how do you think about data compression? Okay. So you have a lot of data. You want to compress that data. First thing always to think about. Is it possible you don't need all this data? Do you really need this data? Maybe just delete it, right? Really, this is very important. And like, that's how like most of the cost savings come from, because you just identify that, oh, I don't need this exabyte of data. Let's just delete the data. And that's basically saving you like millions of dollars. Okay. So again, maybe you can't delete the whole thing, but maybe you can identify with whatever you have learned that some parts of the data are costing you more than other parts of the data. Let's say you are writing a log. Maybe there are multiple fields in the log, let's say. Maybe some fields are much more compressible. Things that look very long, like if you have a log of some sort of web server log, for example, it will have like the host name. But maybe the host name is the same for every log line, because the host name is the name of that host, right? It's the IP address of that host. So anything that just keeps repeating is going to be very compressible, even if it looks long. But maybe there is some request ID or some access ID or something, which is like a random small string. It looks very small when you look at it in the uncompressed domain, right? If you have like if you have host name, which is like 10.1.1.12, something like this. And then that just repeats every line. So this is like, even though it looks long, it's like easy to compress. It doesn't take any bits in the compressed domain. But maybe you have this like random thing, XYA, CXX, BDC, something like this, right? This is very hard to compress. So that sort of thing, like after you do a compression class, you should have some intuition that like, does my identifier, my UUID, some unique identifier, does it need to be so random? Does it need to be 64 bytes? Can I do it with like 10 bytes? Can I make it sequential instead of random? So just like, this is how you can think about it, right? For any type of data, just to plug as an example. If you're storing this data, right, and again, I'm thinking more from like a company perspective rather than personal storage. But even personal storage, right, you take these photos, do you need all of them to look at them really? So for companies, obviously, sometimes there are legal requirements. You need to keep some data for some time, or maybe there are reasons you want to keep it. So sure, okay, maybe you need to keep the data, but think hard about this. And finally, think about like, what is your data access pattern? Take photos, for example, right? Photos, maybe you want to keep them. Maybe in future, at some point, you want to look at them. But it's not like you're going through your like 1-year-old photos every day. So maybe you store it in a cheaper cold storage sort of thing, rather than storing it like in the most expensive storage, right? So just like a computer, if you have read about cache in your computer, right? It keeps the things that are more frequently accessed in a very sort of expensive storage. And it keeps everything that's used less in like RAM or on disk or something. Similarly, store your data in that way. And finally, for a lot of types of data, you can't do lossless compression and be like practical. Videos are the prime example of that. And that's basically the next half of the course, where Sometimes just lossy compression, it's just unreasonable to do lossy compression. So, okay. And one more thing before you like get too discouraged, right? Why do we learn all this if we are just going to delete all our data? Compression is not only about storage. It reduces memory, it reduces bandwidth. You can sometimes query your data faster with compression. So many times you need to do compression, and you need to know how to do compression. Okay, any questions? Yeah. Some of this might sound like a joke, but like when we talk to people, and like this is what the unique thing you can offer, like once you know about compression. Many of these things are not at all obvious to people, like this thing where people think that, oh, this is so long, this should be very like hard to compress, right? But now you know that the entropy here is like 0 basically, because everything is the same, right? You can easily predict the next one based on the previous one, where here you have a lot of entropy. Predicting the next one is not because they are random actually, right? So this is a sort of intuition that will be useful like when you look at a real application. Okay, so now you decide, okay, I need to store this data losslessly. Now what? Now what's the next step? Things not to do. Okay, so maybe you think, okay, I learned EE274. Now I'm very like smart. I will just implement my own compressor, right? I will like use LG77 and I will use Huffman, or maybe I will just design my own LLM or something. Okay, don't do this. And I will talk about why. Or maybe you think, okay, I will not implement, like I will not discover a new algorithm or invent a new algorithm, but I know all these LG77 entropy coders. So let me implement them, right? Let me implement them from scratch in Python or in C. Or maybe you say, no, I'm just not up to it. I didn't like listen in the lectures carefully enough. I will just Google search online and like see some like very expensive compressor and just buy the license to it. Or maybe you just like listen to some small part of this lecture, you decide, oh, LG77 is universal. gzip is an implementation of LG77. It has to be the perfect compressor, right? You didn't listen to the lecture very carefully. And okay, and that's the popular thing, right? Everybody says gzip is the compressor to use. Okay, sure, we'll use that. So don't do this, right? Use your like skills from this class. All of these can make sense, but not as the first step. The first thing you should do is to understand your application. Why are you using compression? What is the need? And where are you using compression, right? So what's the speed you need? What's the memory usage you need? Where is the compression happening? Is it happening on your own machine? Is it happening on somebody else's machine? Is it an open source library? Is it a closed source thing within your organization? Is it like a hobby project? Is it like something that needs to be used in production on like gigabytes or petabytes of data? How will compression and decompression happen? We don't talk about it as often, right? But gzip, zstandard, all of these have a CLI. They have a command line interface. You can like run it like zstandard -c, whatever. Or they have a library. There is a C library, Python library, Java library, all languages imaginable. There is a zstandard or a gzip library. So where will it happen? Is the data homogeneous, right? Like, so for example, do you have like a lot of genomics data? So all of the data looks similar to each other. Or are you like a cloud storage service where everybody wants to store their data on your system? So therefore the data is not up to you. Everybody else decides what data they put in your thing. So whether the data is homogeneous or not will influence how you design your compressor, right? If it's homogeneous, if you have a lot of the data of the same kind, you have lots of genomics data, maybe you want to design your own special compressor for genomics. But if it's not homogeneous, so other people are putting in their data, you don't know what the data is going to be. So then maybe you should use a universal compressor like LZ, right? So all of this should influence like how you think about building your own thing or not building your own thing. So one thing I find often useful is to use these benchmarks that other people have done or you can do. The idea is that you take some corpus, you take some data set, like maybe you take genomics data, maybe you take a mixture of different types of files. You run a bunch of different compressors in their different parameters, and then you make a plot. So you make a plot like this one. So the x-axis is compression speed. So this is better basically. Let me just write faster compression. And this is more compression. And you see, for example, that if speed is your thing, LZ4 is the way to go. There is nobody like even close to it. It's just like several times faster than everybody else. Maybe if you want like the extreme compression, then these things called Z-Pack or C-Mix or these very, very slow but very powerful compressors, maybe those are the way to go. Maybe you want something in between. So maybe you want to use Z standard. Maybe you want something slightly slower than Z standard that gives you better compression. So maybe use BZip2 or BSC. These might just sound like names to you if you have not heard of them, but basically like these are the popular compressors that many times people would want to consider. In this plot, this green one is gzip, this brown one is Z standard. Would you ever use gzip over Z standard by looking at this plot? Right, the top right is the better direction, right? And you see like just Z standard, every level of Z standard is just better than, Z standard just gives you a better Pareto optimal sort of frontier as compared to gzip, right? Because it's like very similar idea, but just modern. It does use more memory. So if you are like running on a Raspberry Pi or you're running on like a 1970s computer for some reason, then you want to use gzip because gzip can work with like even kilobytes of memory versus Z standard would at least take megabytes. When I was small, I had a computer which was like 128 MB total RAM. So there I could imagine like Z standard might be too expensive, but really today it's not that common. Same for decompression speed. So this is like faster decompression, and this is more compression basically. So again, the y-axis is the same. And here you again see LZ4 is the clear winner, right? Fast compression or fast decompression, just use LZ4. Don't worry about anything else. All of them have like multiple parameters, so that's why you see multiple points corresponding to the same thing. Z standard is very fast, Brotli is very fast, gzip is slower but still pretty fast. And the reason is all of these are based on LZ77. And LZ77...
So what about the memory usage for gzip and Z standard?
Yeah. So Z standard uses more memory because it by default uses a bigger window than gzip. Gzip, the maximum window is like, I think 32 kilobytes or 64 kilobytes, something like that. Z standard, you can increase it to even gigabytes if you want to, but by default it's like a few megabytes. So the memory usage of Z standard is like in tens of megabytes typically, whereas gzip is like a couple megabytes or less. So that's the rough like thing. Most applications today, I think, are fine with the Z standard memory usage, but if you're in a very constrained host or like constrained system, then you might not be able to do it. Yeah. So that's like a trade-off they made. Like it's not like Z standard is just better on every front. There is still like the memory front where it's not so good, but I think it's just made for a modern age where gzip like made some decisions. For example, they fixed their maximum window size to be this 32 KB or 65 or 4, I don't remember. There is no way in the format to allow it to increase. Z standard learned from that lesson. They don't put an upper limit on the window size. They say maybe in future there will be a machine which will be able to handle a 1 gigabyte or a 1 terabyte window. Why not let it use that? So there are like these decisions that people make. So I think Z standard was much more careful in like making these decisions on like what the format is in that sense. You can use Z standard with a very low memory if you use a very small window. And then if you want more compression, but you're fine with slower decompression, use BSC or BZip, which I will talk about in a second. But yeah, so the point I was making was that LZ77 is fast at decompression because the decompression, as you saw before, is just copying from the past. And mem copies are very fast. There isn't like a lot of logic there. You do Huffman decoding, you do ANS decoding, all of them are very fast. And then you just copy stuff from the past. So general rule of thumb is Z standard has a very fast decompression at any level. It has a lot of levels. It should be the first thing to try, I think, in today's age. If you are given a compression problem, try Z standard first. And don't use gzip unless you have a very good reason. Maybe you have some compatibility reason. A lot of people have. Like if you are writing data that other people need to read and they don't have Z standard on their system, then maybe you need to write gzip. But other than that, really don't use gzip. To go even faster, try LZ4. So what LZ4 does different from Z standard is that LZ4 has a very fast match finder and it doesn't do any entropy coding. So it skips the ANS or the Huffman step. It just encodes it with some fixed number of bits. So it's so much faster in that way. Now, if you want to go a bit slower, right, you think that, okay, I need to store this data for 10 years. I don't like work with it so often. It's more for an archival type use case. Maybe you want like a better compressor. So now there are two choices mainly. Like one is this LZMA based compressors, which are again LZ77 followed by arithmetic coding, which we know can be more powerful than like Huffman or ANS because you can do context based coding. And XZ, if you have heard of it, or 7-zip are like prime examples of this. Or you use something called BWT based compressors, which we didn't talk about in the class at all. I will let you look at it in the homework. There is a question in the homework that will teach you about BWT. Burrows-Wheeler transform. It's a way to transform the data to make it very compressible. Right. And BWT is faster than LZMA typically at compression, but slower at decompression because the decompression is no longer just copying. It does more advanced things. And then if you're even more resource intensive, you should do like make your own model, do context-based coding, which we learned in the last lecture. And then if you have like nothing to do, like you're just sitting idle, you're okay to have your data be compressed in 100 years, use these super small compressors. This is today, right? Maybe 5 years later, things will change. Maybe we'll have GPUs on every machine or something. Anyway. Right, and now if you decide you want to use Z standard, you want to use it correctly, right? Use the latest version, obvious thing for any software. Or like latest stable version, obviously, yeah. Choose the right level, right? There are like levels 1 to 19, there are negative levels, there are some ultra levels above 19. There is a big range of compression speed, compression ratio trade-off you can choose with Z standard. And sometimes you want to go beyond this. Maybe these levels are not enough. As we saw in the past, right, you have the hash length, min match length, ... all these parameters. Levels are just like specific combinations of these parameters. You can go even deeper. You can like define your own Z standard custom encoder by choosing these special parameters. You can use the CLI, you can use the library in the language of your choice. This is like a common mistake that people do. Like if you are using Z standard in like C or Java or Python, Rust, whatever. If you are compressing multiple files one after the other, you don't need to like drop or delete your Z standard context every time. You can reuse it. So that speeds up your application quite a bit. If you're like compressing a bunch of small files one after the other. And then if you have very, very small files where you don't expect to find good matches within the file, you use something called dictionary compression, which is again a problem in homework 3. This is a very, very interesting topic, which I hope you will enjoy. Also has some of my favorite cartoon characters, so that's good. Okay, and I think this is the last. Yep. Yep.
A follow-up question on so the standard is better than GZIP. Is that only true because we have much bigger, like in terms of performance, we have much bigger context window in which we can find matches? Is it still better if we limit it to 64 KB?
Yeah, it's a good question. Is Z standard only better because we give it a bigger window? No, there are many things they do. One thing is they replace the Huffman coding used for the match positions and lengths with TANS, which is a better compressor, as we saw, right? It was much closer to arithmetic coding. So that's one thing. Then Z standard has many more advanced match finding strategies, many of which actually only make sense at longer context windows. So GZIP uses a very simple hash-based match finder. Z standard has many other things there. And the last thing is the Z standard is just written better. Both the compressor, the decompressor, the format, all of which is written in a way to minimize the number of loops. Loops are very expensive in modern hardware. So they did it in a way which is like very suitable for the today's architectures, the computer architecture stuff. So all of that basically contributes. See, it's not like you shouldn't think Z standard is better compression than GZIP. It's like at the same compression ratio, Z standard is faster. Or at the same speed, Z standard gives you a smaller file, right? So basically when Z standard is doing the same thing that GZIP is doing, it does it faster. So that gives it a boost basically, right? So it's not only better compression, it's also better speed because they implemented it much better. Because the architecture's changed over time, right? It's important. Like we are not saying GZIP is bad. Like when it was made, it's a very, 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 very efficient piece of code for the 1990s. Today, like that's not like the thing you want to use. So last point is that, okay, now you looked at all of those, you still think, no, I have like exabytes of my data. I want to make something special for my data. Or I have like genomics or some special application. I want to make my own compressor. So just a few things that you want to think about before you start making your own compressor. One thing is that you checked out Z standard and gzip and bzip2 and all of these, and you found that the gap between them and your estimate of the entropy. You can build your own models. You make your probability model. You try to estimate what is the entropy of my data. And you see, oh, Z standard gives me 100 kb, but my entropy is around 50 kb. So there is like a 50 kb gap between the entropy and my data. So therefore, maybe I can do better. So that's sort of one thing. Another thing is that, okay, Z standard gives me very good compression, but it just wastes a lot of time because it doesn't know that my data is a table, or my data is a genomic data, or my data is a CSV file, or it's like some specific type of data. So maybe if I know that Z standard is a general purpose compressor, right? So it has to work for every type of data, but your special compressor only needs to work for one kind of data. So it has more flexibility in the design. It can do things that Z standard cannot do because it knows that your data is going to be a CSV file, or it's going to be a genomics data set, or some other thing. Another thing is like if you're going to make your own domain specific compressor, it's easier if it's like a closed ecosystem. You're working within a company or something, because it's not just about the compressor, right? If there are like 100 different people reading the compressed files with their own libraries, their own tools, you suddenly break everyone. As soon as you say, oh, I'm not using gzip or Z standard, I will use my own like .Shubham or something like that, right? I will make my own compressor. I will just use my own compressor, but the other people don't know how to decode your compressor. So how will that work? So your thing will only work if it's a closed. It's much easier to work if it's a closed ecosystem. And final thing is like it's only worth it if you have a lot of data of that kind, or you can't live without it. Basically, you should have a very strong case, because a compressor needs design, it needs implementation, it needs a lot of testing. You need to create a compression format, right? You did that float question when you did the assignment, right? It was so tricky to like store those floats. So many different ways of doing that with all their trade-offs. Think about like a full-fledged compressor. So many different choices you need to make when you like define the format. And once you define the format and you say I'm at version 1, then you're stuck basically. Then you should not change your compressor. If you change your format, then your other people's decoders will break and everybody will be very unhappy. I got a Z standard file, but your Z standard decoder is not working. So just you need to be like very careful about backwards compatibility, that sort of thing. You need to monitor how it's working. You will find bugs, right? gzip, even if it's like 30 years old, they found a bug in it like last year. So it's still like, you need to maintain it for a very, very long time. And then you need to not only implement it once in C or Python or something, you need to have it be supported in like, you should have a Java library, you should have a C library, Python library, ... You need to have it work on like today's machines. You need to have it work on like yesterday's machines and like 30-year-old processors, different architectures, different operating systems. So yeah, only do it if it's worth it, basically. That's the point. In a big company, you can often find cases where it is worth it. Or if that is your whole product, maybe you find a case where it is worth it, right? Genomics, for example, is a domain where there's a lot of data of the same kind, and it is definitely worth it doing a custom compressor, and they did it basically. But then everybody writes a paper improving it slightly in a breaking manner, but nobody uses those particular things, right? Like basically, if you have 1 million different domain-specific compressors, how is anybody going to interoperate, right? Like we have our language like English or any other language. If everybody decided I will use my own language, that's not going to work. So just, there is a limit to like when domain-specific compressors work, but they do work. And if you have a domain that you're interested in, and if you think a domain-specific compressor is the right thing, please come to us and we'll do a project basically. Yeah, do a project on that basically. Last year, like people did on MRI data, I think, and a few other types of like specific data that they were working with. So that's all on lossless compression. Pulkit will see you on Wednesday. Thank you. Thank you for your patience.